So this is a representation of a plasma membrane, and that is a plasma membrane. And in the middle here, we've got the cytoplasm. And over here, in green this time, we've got the dendrites, looking a little bit less like an arachnid, and the axon, and then the axon, oops, very poorly drawn. The axon terminals, boy, that really is horribly drawn. And then we've got this representing that, or that is represented as a blow-up. And so we've got this thing called a sodium-potassium pump. And the sodium-potassium pump takes 3 sodiums and moves it out of the cell, and 2 potassiums and moves them into the cell. And this has the effect of making the interior of the cell have a negative charge and the exterior of the cell have a positive charge. And that's an electrochemical gradient. And as a consequence of this, the positively charged things want to get into the cell very badly, because opposites in electrical charges attract. So positives want to come to negatives, or negatives want to go to positives. And in fact, this is the basis of how a battery works, although in this instance we're not talking about this within the context of a battery. Although in other instances inside of our cells we do have electrochemical gradients that are used as batteries, and that has to do with mitochondria and the generation of ATP and stuff like that. But in this instance what we have is essentially a potential. We have something that wants to happen, but it's being prevented from happening because you've got this membrane in between. The membrane here, in a sense, serves as an insulator. It prevents the positives from getting together with the negatives. Now, if you have something that intervenes, that allows the positives to get together with the negatives, then you can lose this electrochemical gradient, and that's called depolarization. At least the initial steps are. And what happens is you've got 2 kinds of channels. There are ligand-gated channels and there are voltage-gated channels. The ligand-gated channels are what we talked about when we talked about neuromuscular junctions. And in fact, they're found at synapses. At the synapse, what you have is a chemical signal that goes from one neuron to another neuron. And what this chemical signal does is it diffuses across a synapse and it binds to ligand-gated channels. And when the ligand, the neurotransmitter, binds to these membrane proteins, these channels, the channels open up. And what they have the effect of doing is allowing the movement of the sodium ions into the cell. And that movement into the cell has the effect of reducing this negative charge. And that reduction in the negative charge is called, I will use green, it's called depolarization. Now we're not quite at an action potential yet, but we're getting there. Now depolarization, if it is sufficient, can stimulate these other channels that are the voltage-gated channels. To open up, and once again, at least this kind of voltage-gated channel, you have sodium ions coming in. And if we have enough sodium ions coming in, that you get enough depolarization, that locally, not globally across the cell, but immediately next to where the depolarization is happening, causes these voltage-gated channels to open up. And that happens if you reach a sufficient level of depolarization, which means that a sufficient number of sodium ions make it into the cytoplasm, that you reach what is known as the threshold potential. So what you have is a depolarization event caused by these ligand-gated channels, caused by the neurotransmitters from presynaptic neurons that are stimulating or instead might be inhibiting the opening of these ligand-gated channels. But if you get enough ligand-gated channels opening up, then you'll get enough sodium ions leaking in that you reduce the polarity of the charge differential across the membrane enough that you'll have reached a level of depolarization that's equal to the threshold potential, and at that point you start opening up the voltage-gated channels. Now, all of this stuff takes time, and what you have basically are voltage-gated channels opening up, and then you actually have other voltage-gated channels opening up that allow the potassium out. So you've got the voltage-gated channels that open up, that allow the sodium out, Enough sodium comes in and that stimulates the voltage-gated channels that allow the potassium to leave to open up. And then you've got, following behind this, the sodium-potassium pump, which restores the original state. And that's actually called the resting potential. So resting potential is the original state. So resting potential can be followed by sodium ions coming up in sufficient numbers that you reach a threshold potential, which then opens up the voltage-gated channels, which bring more sodium in, which then stimulates the opening of further voltage-gated channels adjacent to the ones that had just opened up. And then behind this opening up of the voltage-gated channels that allow the sodium to come in, you have voltage-gated channels that allow the potassium to come out occurring. And then behind that, you've got the restoration of the original system getting back to the resting potential. So you've got these initiation events, but then you've got this wave of three things: letting sodium in, letting potassium out, and restoring. And this wave and this order is important because the potassium is not going to come in until the sodium is going to come in, and you're not going to restore the resting potential until the potassium comes in. So you have these different states that can only be followed by specific other states. And the result of that is that you can get propagation in only one direction. You can't go backwards. If you have the opening, letting sodium coming in here, that can't go backwards until you reestablish the resting potential, but that takes time. So that can only go in one direction. And the same thing with the potassium going out, follow behind it with the reestablishment of the resting potential behind that. So the result is this wave of depolarization and then ultimately repolarization. Depolarization happens when you let the sodium in enough, or when you let sodium in. Repolarization happens when you let the potassium out, and then you have, following that, the reestablishment of the resting potential. You have this wave of this going on from one end of the neuron to the other end of the neuron, and that wave is the action potential. And I only understood that over the course of the past week. I mean, I understood all the parts, but either I didn't remember it, or in my mind it never occurred to me that what we've got are three states, and the states can only they can only follow each other in a specific order, and it's that requirement that they have to follow each other in that specific order that guarantees that the action potential starts in one place and then moves to another place, but can't go backwards again. And then it takes time for the resting potential to reestablish, and this means that you have a nerve impulse, an action potential, but then you have to reestablish the ability of the neuron to conduct a nerve impulse, and then you can have another nerve impulse if you get a sufficient amount of stimulation. So the difference between a neuron telling whatever's downstream, whatever information it's carrying to whatever's downstream. The difference between a lot of information being carried and not a lot is not the intensity of the action potential. The intensity of the action potential is always the same. Instead, it's the frequency of the action potentials. And this is, for example, we saw with our muscles. The muscles are a relatively easy system because when you have an action potential neurotransmitter release, you get an action. It's none of this summation stuff. And so as a consequence, if you want to get a lot of muscle activity, you don't have bigger action potentials, you have more action potentials. But there's a limit to how much action potential you can send down to neurons. But if you want more signal going down, it's not a bigger signal that goes down, it's more signals that go down.